Okay, so the last of our trig functions or circular functions that we need to sketch is the tan graph. So you can see there from the diagram that we've got, it's very different in the way it looks to the sine and cosine graph. A couple of things that we should note in particular here, the tan graph itself has a period of pi, so it repeats itself every pi unit. So if you have a look here, we refer to these as asymptotes, and we've seen asymptotes before. So my vertical asymptotes, the distance between the asymptotes here is pi. Okay. Other key thing here to note is that this graph continues onwards indefinitely. Okay, so my tan graph has no amplitude. All right. So it starts at the origin, continues up towards pi on 2, comes down as we head towards negative pi on 2 in terms of the x values. All right. So my tan function is undefined. If you think about it, tan x is equal to sine x on cos x. So wherever cos is 0, my tan graph is undefined. So that's at the cos is 0 up here, isn't it? At pi on 2 and 3 pi on 2, etc. So you can see there, asymptotes at plus or minus pi on 2, and the intercepts every value of pi. All right. The general formula for my tan graph, okay, so for tan 2x, tan 3x, etc., is given by pi on n instead of 2 pi on n. The range of the function is r. Look, we can remember rules for our asymptotes and our intercept, but I prefer to sketch the graph, sketch one cycle, and then just repeat everything every period the way in which we've been doing. All right. So let's have a look at what that might look. So we can see here we've got the graph of tan 3x. We'll put it there. We want that one. So again, first things we identify is the period. For the tan graph, it's pi on n, which for us is pi on 3, which means since we're not shifting left or right anywhere, so the distance between asymptotes is pi on 3 units. So that means my first asymptote at pi on 6 and negative pi on 6, because the distance then is pi on 3. So let's just make our axis a bit bigger. Pi on 6 is not the greatest again. They haven't given us the best scales to work with. So if that's pi on 4, that's the same as negative 3 pi on 12. Pi on 6 is 2 pi on 12. So I reckon, what if we just cheat a fraction? Let's cheat. Negative pi on 6, pi on 6. Yeah, I reckon that works better, because that's sort of the way in which I want you to do it anyway. Just put a cycle in, and my tan graph comes up to there and goes down to there. So the period is pi on 3. So if that's pi on 6, let's go. Let's pi on 6. We'll call it 2 pi on 6, 3 pi on 6, 4 pi on 6, etc. So 1 pi on 6, 2 pi on 6 is there. So my graph repeats itself here. The asymptote again, the distance between asymptotes has to be pi on 3. So once again, we get one cycle. Everything just repeats itself. Yeah. And then finding for x-intercepts or solving our tan function is exactly the same as solving our sine or cosine functions. Whereabouts is tan -1? Well, tan is negative in this quadrant and this quadrant. So they're the quadrants that we're in. They're my angles. So x is tan inverse of 1, which is, give you a moment, pi on 4. Let's get our first solutions. So let's just start at 0. That's 4 pi on 4 around to pi. 8 pi on 4 there. So my first solutions x are equal to 3 pi on 4 and all the way around to 7 pi on 4. If I just add and subtract the period, okay, is pi on n. So the period of my domain of my graph is pi. So if I subtract pi and add pi, which is 4 on 4, my next two solutions, if I subtract 4, I get negative pi on 4. If I subtract another 4, I get negative 5 pi on 4. And obviously the 7 pi on 4 is already too big. So the solutions that fit in are 3 pi on 4. Well, let's put the negative one first. Negative pi on 4 and 3 pi on 4. 7 pi on 4 is outside of pi. Negative 5 pi on 4 is outside of negative pi. Okay, so let's keep working through. Same thing for tan 2x. Tan is positive, however, up there and down there. Tan inverse of root 3 is pi on 3, which is 60 degrees. So pi on 3 there, pi on 3 there. Let's get my answers, which are 2x. So 2x is equal to my first two solutions. A pi on 3 around to pi plus pi on 3, which is 4 pi on 3. And so that means x is equal to pi on 6, and we'll leave it as 4 pi on 6. So now to get the rest of my solutions, I need to add and subtract the period. So the period of this graph is equal to pi on n, which is pi on 2. And since we're working with sixes, we'll call that 3 pi on 6. So now let's add and subtract all my other, add and subtract the period from my other solution. So pi on 6 minus 3 is negative 2 pi on 6. Negative 2 minus 3 is negative 5 pi on 6. Take another 3 off, it goes to negative 8. That's going to be too big. I've got 4 pi on 6. If I add 3, well, that's 7 pi on 6, which is too big also. So we can see there, they're my 4 solutions, all right? So get your first two solutions, then add and subtract the period of the function. 2 tan 3x, okay, so it's going to be very similar to the others. First things first, whereabouts is tan negative? Well, tan is negative on the horizontal axis, yeah? If I divide both sides by 2, I'm still looking to solve tan 3x is equal to 0. So that means 3x is equal to my first solution, which is 0. My next solution there, which is pi. So x is equal to 0 or pi on 3. So again, add and subtract the period. Period for tan 3x is pi on n, which is pi on 3. So if we add and subtract pi on 3, if I keep adding first, I get 2 pi on 3 and 3 pi on 3. Then if I subtract from 0, I get negative pi on 3, negative 2 pi on 3, negative 3 pi on. Job done.